Hey guys, today I want to take a look at power series. We're finally getting to the punchline of what we've been working at in the last unit with all the convergence and looking at all these different tests and stuff for series. Remember, our goal was to be able to represent transcendental functions by writing them as infinitely long polynomials. So power series is actually getting to it. So let's see, a power series is a series of the form a sub n x to the n. That's simple. Now, we recognize series of this form, or we've seen ones of this basic form. We're familiar with this guy. That will converge for absolute value of r less than 1, right? This is a geometric series. So we can leverage this to get a bunch of them right away. But let's back up a second. We'll leverage this just by saying that this x is going to act like r, right? So we can force that to converge for absolute value of x less than 1. Okay, well, we'll get to that. Let's see. We do have another form that we need to worry about here. N equals 0, a sub n, x minus c to the n. This is also a power series. This power series, remember the a sub n's, these are just constants, right? That's a sequence. Here our power series is centered at 0, and here our power series is centered at c. Okay, so these are just constants. This is a sequence, and this is our center. Okay, now some functions like, say, 1 over x, we're not going to be able to center that at 0, right? Because 1 over x will blow up at 0, it'll diverge. Or ln at 0 is undefined, right? It's negative infinity. So again, we're not going to be able to center our series at 0 for like ln. For most series, though, we'll be able to center at 0, and we get a much simpler looking sort of series. Yeah? Okay. The other advantage of center, or the usage of center, is that a lot of times these will only converge on a finite interval. I'll actually write that here in a second. So they may or may not converge on an interval where we're interested in. Say we have this series and it converges on the interval from, I don't know, 1 to 10, and we want the value at 25. Well, we know it's going to blow up at 25, so okay, we'll just shift the center over and we'll be able to get it to converge on the interval where we're interested. Okay, so that's the deal with the center. Now, let's look at this. If I evaluate this series at the center, right? If I plug in x equals c, all these terms that have x's in, or if I plug in 0 here anyway, if I evaluate at the center, all these terms are going to zero out except for a sub 0. So clearly, at the center, this series will converge. Always, always, always. So that's one possibility, is that our power series converges at a single point, only the center. But it's always going to converge at that center. Okay? Another possibility is that it converges absolutely everywhere, the entire real line. That's really nice. We'll see that for things like e to the x, the sine x, cosine x. These guys converge on the entire real line, so we don't have to worry about it. We can plug in any x in there, and it's going to converge to the correct value. Never going to blow up on us. And the third possibility is that we have convergence at the center and then some finite interval around that center. Now, the endpoints are contentious. We always have to check the endpoints. It may or may not converge. We might have a half open or clopin interval, or it may be closed, or it may be completely open. We have to check those endpoints. But essentially it's always going to be in between these finite values, okay? So this is going to be what? C, we'll call this C minus R and C plus R, where R is our radius of convergence, okay? So it's going to converge for some absolute value of x minus c less than, it may be equal to, but less than this radius, okay? So those are the only three possibilities with these power series, which is sort of nice. And in the sense that we're never going to get these weird, like, disjointed intervals or anything like that. It either converges right at the center and center only, converges everywhere, or it converges on a finite interval surrounding that center. Of course, the endpoints, again, we got to check those. Okay. So at least they're somewhat well behaved in that sense. We don't have to go hunting around for a bunch of different intervals. We can, speaking of that, how do we find this? Generally, either we're going to leverage the fact that we're working with something similar to a geometric series and use the fact that the absolute value of x or the absolute value of r needs to be less than 1, force it that way. And the other way that we generally use a fallback tool is our ratio test. Remember, our ratio test, we look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So we're just comparing two terms in the same sequence, and we're taking their limit, absolute value, which is nice because that gives us a test for absolute convergence, which then implies convergence. Okay, now this will converge if that's less than 1. So that's kind of the fallback tool that we end up using if we can't just see it as a geometric. We'll just run that limit, see when and where it is actually less than 1, or force it to be that way, and then we'll know on what interval it converges. Okay. So that's sort of in general definition of power series, the intervals on which they converge. The other real nice thing about power series is that when we get the base ones, let's say I have, the power series for sine of x, then we can leverage that as well, that we can use that series and simply evaluate or multiply, okay? So to get new series or new functions. So if I want the sine of x squared, well, I already have the sine of x series. All I need to do is plug in x squared, and we're done. Evaluate, literally, plug and chug. So some of those things, let's say if the series a sub n x to the n is some function. Okay, so we have this power series and it converges to some f of x. Well, then I can multiply by a constant, let's use k, and a power of x. So let's use capital M. Okay, so if I can take a constant and some power of x, so basically a monomial term, multiply that by my function, well, that's the same as taking my series, a sub n, k x to the m, x to the n. Nice. So I'm basically just multiplying the constant and the power of x through. All right, same deal if we have f of k x to the m. So this is what I'm saying, I can evaluate at a constant or a power of x. That's going to be a sub n, k to the n, x to the m, n. Power to power, right, I multiply. So I'm just evaluating, I'm just plugging in whatever my constant power of x is, and then here I'm just putting that n power onto the constant and pulling it out with my sequence terms there. Okay, and then we can also add and subtract them, which is really nice. Actually, I probably need another one of these then. Let's b sub n x to the n, and we'll call that some g. Then if I have f of x plus or minus g of x, that's simply the sum or the difference of the two series. And we can combine those together real nice so that I have a sub n plus or minus b sub n x to the n. And of course, is, by distributive property and all that business. Okay? So they're very, very powerful tools. Once I've got a base series, a base function, getting variations on those is almost mind-numbingly easy. Yeah? Just plug and chug. One of the other advantages to these that we'll see is, it gives us a way to actually calculate these transcendental functions. Like how would you calculate ln of x if you didn't know how to do it? Or how would you teach a calculator to do it? Well, this gives us an actual polynomial process by which we can calculate those values. And they converge really, really fast, which is a bonus. So we don't have to do these all day long. Usually 3 or 4 terms and we're good to whatever, 9 decimal places or whatever we need. Okay, the other really nice advantage to power series, once we have those base series, we can get the integrals and the derivatives simply by integrating and differentiating term-wise. Okay, so if I have, the integral of f of x dx is going to be the term-wise integral. So let's say, what's the best way to write that? Well, we have that it's equal to, I want to integrate it. Let's just say integrate series term-wise. And likewise, if I have the derivatives, right, we'll differentiate term-wise. All right, so if we had 1 over x, if we have the series for 1 over x, then I can integrate that to get the series for ln without having to know how to get the series for ln otherwise, just by integrating term-wise. So let's try a couple. Let's take a look and see how we would deal with some of these. Those are some of the general properties, definition of what a power series is and how they work, some of their advantages and what we can do with them. Let's try a relatively simple one. Let's say we have, let's start with the easiest one. We've got our function 1 over 1 minus x. Now, it's kind of weird. This isn't the most pretty rational function, I guess, but it's the simplest series on the series side. So when I look at this, I'm thinking about the geometric series, a over 1 minus r. And I want whatever's here to play the role of r, because I know that this will converge for absolute value of r less than 1. Yeah? So I look at this one and I go, oh, well, nice. This is already in the right form here. A's got to be 1. The minus is already there, so r is just x. That means I've got the series n equals 0. A is just 1. X to the n. And I know that this will converge for the absolute value of x less than 1. So it's just, 1 plus x squared plus x cubed plus and so on, right? Sort of the simplest one on the series side. Cool. All right, so we have the series for 1 over 1 minus x. That's our first function that we can look at. Now, from there, we could get the series for, say, let's say our function is 1 over 1 minus x squared. Well, 1 over 1 minus x squared is the derivative. Be careful there, it's chain rule, right? So we would have a negative in here, but then the derivative of our u, or our inside, is -1, so this is legit our derivative. Say, well, okay, if that's the derivative of this, then I can just term-wise differentiate everything here, which means that this is going to go, right, this is going to become a 1. This is going to become, well, this is 0. That's a 0, plus 1, plus, what, 2x, plus 3x squared, plus, right? So I'm just taking the derivative term-wise here, and now I say, oh, well, if I want to start at 0, if I want to continue starting at 0, that means I will have n x to the n minus 1. Yeah? If I wanted to start at 1, I just need to shift that index over. But otherwise, this is going to work, right? 0 times 1 over x, so 0, and then 1 to the 0, yep, 2x to the first, we're good to go. So if you notice, this is just straight power rule, right? N times n minus 1, n x to the n minus 1. So we're literally just differentiating that term by term. All right, so there's a couple straightforward basic ones we can get right away. Let's see, those ones are centered at 0. Let's try a super important one, 1 over x. It's our harmonic, right? 1 over x. So let's see if we can find out what the series is for that. Well, we're on the path of trying to do a over 1 minus r. So I want this to be 1 minus. I want there to be 1 minus down here. So I need to add a 1 and subtract a 1. Yeah? That just is compensating for the fact that I want this 1 here. Yeah? Now let's see, if I pull a negative out of here, I can make this a minus. Flip my signs around there, because I pulled a negative out here. Now it looks like I've got the right form. A over 1 minus r, where this is going to play the role of r. All right, my a is just 1. And you can either write it 1 minus x to the n. So there, we can call that done, but it's not really clear what's going on there or where it's centered. So we can just pull a -1 out of here. And that becomes an x minus 1 to the n. And now it sort of becomes clear that, okay, this thing is centered at 1. Which is good, because we couldn't center 1 over x at 0, right? It would diverge, it would blow up. So there we've got our series for f of x, or 1 over x, excuse me, the harmonic. Which means that then we can get ln super easy. Because ln is just the integral of 1 over x, which means I need to term-wise integrate this. Now there is a constant of integration there. Let's see, let me write it here. Let's say our function is ln of x that we're looking for. And so we're going to integrate this guy, which means I'm going to integrate 1 over x dx. And I'm going to get some constant plus series, well, I just need to integrate this term-wise. So add 1 to the power and divide by the new power, right? Super easy. -1 to the n, x minus 1 to the n plus 1 over n plus 1. So there I've integrated term-wise, right? Add 1 to the power, divide by the new power. But I do have that constant of integration sitting out there. Say, well, okay, let's evaluate this thing at the center. Remember, this is ln, oops, this is x minus 1. Is equal to this, right? So when I plug in 1, I'm going to get ln of 0. This stuff all zeroes out. So I get that, well, let's see, ln of 1 minus 1. No, that's ln of 0. Shoot, what am I doing? No, that's because I was right originally. That's why. Okay, it is ln of x, so I'm evaluating at ln of 1, which is 0. All the rest of the stuff zeroes out, and so we get that c is 0. There we go. I shouldn't have made that change, sorry. Okay, so we get that our original c, the constant of integration is 0, so that's actually just gone. And there we've got our formula for ln. So let's put those somewhere, because those are a couple of our basic. So we had 1 over x is the series -1 to the n, x minus 1 to the n. And we have that f of x equal ln of x, which is the integral, is the series n equals 0, -1 to the n, x to the n plus 1. Oops, I forgot one. Minus 1. To the n plus 1 over n plus 1. There we go. Okay. And then, of course, we had our original one. If f of x is 1 over 1 minus x, that's just the series x to the n. That's the most straightforward one, the simplest one on the series side. And let's see, let's try to combine a couple of those. We've gotten some of the basic ones, 1 over x, ln, 1 over 1 minus x. I suppose we could do 1 over 1 plus x pretty simply. All we have to do is evaluate at -1, right? Because if I have 1 over 1 plus x, that's 1 over 1 minus -x. But I already have the series for 1 minus x, so I just evaluate at -x. No problem. That's super easy to get. So 1 over 1 plus x is the series I just lost it. Oh, -1 to the n, x to the n, of course. Flippy floppies. We just plug in the negative version. Okay, good. So those are some of the basic ones. Let's try out a slightly more advanced one. Kind of combines these two ideas using the geometric business and integrating or differentiating term-wise. Let's see if we can find the series for arctan. Or arctan. Okay. So let's start with the fact that the derivative of the arctan, is 1 over 1 plus x squared. Right? Okay, so we have that knowledge already, which means that I can use the geometric stuff to figure out what the series is for the derivative. And then I just need to integrate term-wise, and I'll be able to get my arctan. Okay, so this is 1 over 1 minus negative x squared, which is going to give me the series negative 1 to the n x to the 2n. Okay. I'm just evaluating at negative x squared. Now this will converge for absolute value of negative x squared less than 1. Well, that's absolute value of x squared less than 1. So absolute value of x, take the square root, less than 1. So it's still going to converge on the same interval. Okay, oops, there's n equals 0. So let's see, this looks like, let's plug in 0, that would be a 1. This is going to be a 1, so 1. Plug in a 1, that's going to make that a minus x squared. Plug in a 2, that's going to make this a plus x to the 4th. And now we can start to see the pattern, right? If I plug in a 3, that's going to be a minus, and I'm going to get x to the 6th, plus, and so on, right? Okay, so there's our series for 1 over 1 plus x squared. Now arctan is the integral, so I just need to integrate those term-wise. So my integral, I got x minus x cubed over 3. I'm integrating, right? Add 1, divide by the new power, plus x to the 5 over 5 minus x to the 7 over 7 plus, and so on. All right, so let's see if we can just generalize that. I have the sum from n equals 0. My signs are still flip-flopping. My signs are still flip-flopping, and the first one is positive. So let's go negative 1 to the n. So I get, on my first term, I get negative 1 to the 0, so I ensure that this is positive. And let's see, everything is odds. So odds are 2n plus 1. And let's see, if my n is 0, then 2n plus 1 would give me x to the first, so that looks fine. 2n plus 1 over 2n plus 1, and let's just double check that we made that right. If n is 1, we're going to get a negative 3 over 3, nice. If n is 2, we're going to get positive, that'll be a 5 over 5, good, we're on the, that's it. Okay, so that is the series for arctan of x. And it will converge on the, well, we know on the absolute value x less than 1, but we need to check our endpoints here. So let's see. What we're looking at right now is the interval negative 1 to 1. We know that much from here. But what if x is positive 1? Well, that'll make this just a 1. I have an alternating series here, and my terms are decreasing to 0. So by the alternating series test, that's enough. It means it's going to converge on the endpoint where x equals 1 by the alternating series test. Boom. Now, what if x is negative 1? Well, I'm going to have another negative 1 to the 2n plus 1. So I'm going to add these together. I'm going to get a negative 1 to the 3n plus 1. Well, 3n plus 1, that's going to flip-flop. Even odd, even odd, depending on whether n is even or odd. So again, we have an alternating series. The terms decrease to 0. So by the alternating series test, that's enough. It converges. And so our arctan actually converges on the closed interval from -1 to 1. Got to remember to double check those endpoints. Good. All right, so we've got some of the basic ones just from playing around with geometrics. Most of these guys were either centered at 0 or 1. Let's try one where we have to fiddle. Let's try say f of x equal to 4 over 3x. Where was that? 4 over 3x plus 2 centered at 2. So here I've got a different center rather than just being at 0. Well, let's do it centered at 0 first. That's super easy. So I'm trying to fit this to a over 1 minus r. So I want to get these to switch. That's not a problem. 4 over 2 plus 3x. Now let's see, I want this to be a minus. So 4 over 2 minus negative 3x. And I want that to be a 1. So I just need to divide by 2. 2 over 1 minus, say, negative 3 halves x. No? We could put that outside that half, I guess, but whatever. Same diff. Okay, so there's our a, there's our r. We've got the series 2 times, we have a negative 1 to the n, and we have 3 to the n, 3 to the n, over 2 to the n, so this would be 1 minus n, and x to the n. Okay. So there would be, that would be it if we were just centered at 0. Okay, so we just went through the procedure of getting this to a over 1 minus r and then back plugging it in. Here I'm just pulling stuff out, like the negative and the 3 halves, and I'm just simplifying that stuff a little bit, just so that this is my constant term, and then I've got my x to the n, and I can see clearly that this is centered at 0. You can still leave the 3 over 2 to the n inside there, and it's still going to be centered at 0. But okay, so that was if it was centered at 0. Now we want to do it if it's centered at 2. So the first thing I'm going to do, still on the same track, let's say 4 over 2 plus 3x. Okay, I can flip those around and get my function going second there. Now, I want that to be a negative. Should we do that first, or should we compensate second? I suppose it doesn't really matter. But we're going to have a lot of negatives flying around. So let's fix this first. I want it centered at 2, so let's go 4 over 2 plus 3 times x minus 2. Here I'm forcing my center to be at 2, but I've got to compensate for the fact that I've just subtracted 6. So I had the plus 3x and then the minus 6. So I need to add 6 in order to compensate for that. Which will give me an 8, 4 over 8 plus 3 times x minus 2. Okay, so there I've fixed the fact that I wanted my center to be at 2. I could have fixed the minus first. That's what I was debating there for a second, is whether to pull this a minus minus, but then I was worried that we're going to have all kinds of negatives floating around. So I took care of the center first, and now I'm going to fix, well, we can fix the 1. It doesn't really matter what order we do it in. We're going to divide by 8, right, in order to turn that into a 1. So I'll get a 1/2 over 1 plus 3x minus 2, and we're close now, right? I need a over 1 minus r, so I just need to fix this to be a minus. Oh, I didn't divide by 8. There we go. And so I'll just have a minus minus, and let's bring this up here. So we have 1/2 over 1 minus negative 3/8 x minus 2, like that. Yeah? So we've got it fit to a over 1 minus r. All this is playing the role of r. So we know that, let's see, let's finish this out. N equals 0. Our a is a 1/2. Now we do have a negative in here, so I can put the -1 to the n. Then I have a 3 to the n, 8 to the n. Again, I could leave that 3/8 inside. X minus 2 to the n. Now let's see, we need this absolute value of negative 3/8 x minus 2 to be less than 1, right? That's the geometric that we're forcing r, this r, the absolute value of that to be less than 1. Well, the nice thing about that is we can get rid of the flippy flop or the negative business. We don't have to worry about that since it's in the absolute value. And we've got what, x minus 2 less than 8/3. And we've got x less than, add 2 would be 6, 14/3. Okay, and then of course we do it on the other side. That would be minus, it's greater than minus. Eight-thirds, and add 2 minus 8/3 is 6/3, negative 2/3. Okay, and then of course we need to double check our endpoints. It's centered at 2. Oh, the other thing to note here is that here we can read this off, that it's centered at 2 and our radius is 8/3. So this interval should be here at 2 and then 14/3 over here, and over here what, negative 2/3, if I've done my math correctly, 8/3. All right, and then we do, like I said, we do need to check our endpoints here. Let's see. I just don't want to do the algebra. Being lazy. 14/3 minus 2/3. That's going to give us a -1. -1, that'll make that positive. I think that's going to diverge on that end. On the negative side, that'll be a negative. That'll make that. I think it's going to diverge at both ends. Maybe do that as a homework. I just don't want to plug and chug and do all the algebra. I'm trying to do it in my head, but whatever. Strictly speaking, we need to check the endpoints, but I'm being lazy. More important is seeing how to deal with shifting this center and then moving it over. All right. So that's power series stuff. Let's talk about Taylor and Maclaurin series. Taylor series. Cool thing about these, they give us a very algorithmic way to start from a function that has n derivatives or infinitely many derivatives and work our way to the series that will converge to that. What we're doing essentially, rather than writing out all the algebra and doing it all out, just to give you the punchline, what we're doing is we're forcing the function value to be the same at the center. So we're saying, okay, here f evaluated at the center has to be equal to this series evaluated at the center. And then we're saying, okay, not only do the function values have to agree at the center, but they have to be changing at exactly the same rate. In other words, the first derivatives evaluated at the center also have to be equal. And then we're saying they have to have the same curvature as well, right? So the second derivatives have to be equal at the center, and the third derivatives, and so on, all have to be equal as many n derivatives or infinitely many derivatives as we have. So what that does is we're continually taking derivatives, right? If I have this n, like some x to the n, that one would be centered at 0, right? And I'm taking the derivative, then I'm going to get n x to the n minus 1, right? And then I take another derivative, I'm going to get n times n minus 1 x to the n minus 2. And I take another derivative, I'm going to get n times n minus 1 times n minus 2 x to the n minus 3. And I keep taking these n derivatives, right? And what I'm getting is n times n minus 1 times n minus 2 times n minus 3, and so on, right? X to the whatever. But this is n factorial, yeah? N times n minus 1 times n minus, all down. So that's where this factorial is coming from. It's coming from repeated applications of the power rule. And since we're forcing these two things to be equal, we end up dividing that factorial over to the other side when we solve. And we get that our coefficients that we need right, what we're looking for, we've got some function f of x, and we want a series representation of that. Now this is a Taylor series, or we're talking about Taylor series. That's in general with any center. If the center is a 0, then it's a Maclaurin series. It's a more particular or limited version, right? Limiting case. Okay, so what's key here are these coefficients. That's what I need to find out. All of this is boilerplate, this x minus c to the n. That's just going to be powers of x minus c and so on, right? So what I'm doing is I'm forcing all the derivatives to be equal and solving for each of these. And what I'm going to get is that when I evaluate the nth derivative at the center, that's going to be equal to, we're going to have this n factorial business over here, right? And then there's like these x minus c over here. No, sorry. These are better. Okay. So I'm taking these repeated derivatives and I'm trying to solve for these a sub n's for each of those. And I say, okay, well, a sub n, the coefficients that I need on each of these terms is the nth derivative evaluated at the center divided by n factorial. That n factorial, again, is coming from this repeated power rule differentiation. Now, for those of you guys who might not have seen that before, this is Newton, right, where f prime is the first derivative, double prime second derivative, triple prime third derivative, and then after that we get lazy. fourth derivative. Now, strictly speaking, we could write this as what, the first derivative, but we generally don't. And then f would be what, the 0th derivative. The actual function itself is the 0th derivative. So that's what that notation means. And we put the parentheses around just to denote the fact that we're talking about a derivative, not a power of that function. Okay, so it's a very, very formulaic, algorithmic way to find out what these power series are. We now know what these a sub n's are, and we get that f of x is the series x equals 0, the nth derivative of f evaluated at the center over n factorial x minus c to the n. And this is the magic formula that's going to, you give me some function, some f of x, as long as it's got n derivatives, I'm going to just use this formula and off we run. That'll force the function value to be equal at the center, and the first derivative, the second derivative, and so on, all to be equal at the center. They may be different, they may get more and more different from each other, these functions and the series, as we get further and further away from the center, right? That in that case, they might diverge. But we're forcing it to be at the center at least, and then in the region around the center, it should closely approximate or be equal to. Okay, so that's it. That's kind of the punchline of all of it. This is the really, really powerful thing. Again, if it's just centered at some c, that's going to be a Taylor series in general. If it's centered at 0, so there's no c's here, it's just x to the n, then that's a Maclaurin series, a limiting case of Taylor series. All right, so let's try one at least, or a couple maybe. I don't know, gotta watch the time here. Let's try to figure out I'm running out of time. E to the x, why not? That's a good one. It's one of our base functions. Now e to the x has infinitely many derivatives, right? It's infinitely differentiable. So what I'll do is I'll say, okay, f, let's center this guy at 0. We have no discontinuities at 0, so that's fine. We can find a Maclaurin series for it. So f evaluated at 0 is e to the 0, which is just 1. Yeah? What's the first derivative? Well, the first derivative is still e to the x. So the first derivative evaluated at 0 is e to the 0, which is 1. Now, that's always going to be the case, right? The second derivative of e to the x is e to the x still. So if I evaluate at 0, we get at c is equal to 1, right? All right. So all those coefficients, f sub n in the numerators, are just 1. So let's see, we have n equals 0. Now our first term, f evaluated to 0, is just a 1. So let's see, well, let's write it out. We've got 1 over 0 factorial, x to the 0. So that's our first term, right? Plus, all these numerators are just 1s. 1 over 1 factorial plus x to the first power. Again, just 1s. 1 over 2 factorial x squared. All right, so it looks like that's going to be a relatively simple pattern. It's just x to the n over n factorial. X to the n over n factorial. Beautiful, beautiful. All right. So there we've got we use the formula, finding the nth derivative and evaluating at the center. That's giving us the numerators on these coefficients. The denominators are always just n factorial. And then it's x to the n, or x minus c to the n, but since we're centered at 0, it's just x to the n. Okay, so that's a really beautiful one. But let's figure out now, where does this e to the x converge? Maybe it only converges at 0. We're like screwed. We only got one value of e to the x. So let's see. For now, what we're saying is this, right? That e to the x is x to the n over n factorial. And I'm interested in finding out, where does this guy converge? Well, it doesn't look like a geometric, right? It's not, I can't do the a over 1 minus r trick. So I'm going to fall back to my ratio test. And I'll say, okay, I'm going to look at the limit as n goes to infinity of the absolute value of a sub n plus 1. So the n plus 1th term is x to the n plus 1 over n plus 1 factorial. There's my a sub n term. And now a sub n term, x to the n over n factorial. All right, so I'm looking at this limit. I say, okay, that's the limit as n goes to infinity. Oops. Stuff is going to flip up and down. So I've got x to the n plus 1 over x to the n, that will go downstairs. This n factorial is going to come upstairs, and that n plus 1 factorial is downstairs. All right. X to the n over x to the n, that's going to become 1. So I just have an x to the first power in the numerator. N factorial over n plus 1 factorial. Well, let's see. This is going to be n times n minus 1 times n minus 2 times all the way down to 1. This one is n plus 1 times n times n minus 1 times n minus 2, and right? Down to 1. So n over n, n minus 1 over n minus 1, all that stuff is going to become 1. And I'm just left with n plus 1 down in the denominator. Nice. Well, this absolute value of x doesn't care about n. So we have that this is the absolute value of x times the limit as n goes to infinity of 1 over n plus 1. But 1 over n plus 1 goes to 0, right? That in the limit. So that's the absolute value of x times 0. Doesn't matter what x is, that's always 0, uniquely 0. Which is less than 1 for all x. It doesn't matter what x is, that's always less than 1. So we've shown that this limit, the limit of the ratio of the two terms in the sequence, is always less than 1 for all x. So it'll converge on the entire real line. It converges for all x. So the entire real line. In other words, negative infinity to infinity. Which is really nice. That means that any value of x that I want to evaluate, e to the x, I can plug it in, we're good. It's going to converge to the correct value. The other really nice thing, and like I said, is you can't put every value of e to the x into a calculator, right? But this gives it a way to figure it out. And it only needs to add, look, these n factorial grows wicked fast. It grows faster than any exponential function. So n factorial, these terms, they're getting really small really quickly, which means they converge very fast. And we only need to try just a few terms. The 10th and 11th term, they're changing in like the 1000th decimal place or something. So they're basically not any use to us. So this gives a really rapid way for calculators to find like ln and e to the x and things like that, because they converge very rapidly. So that n factorial downstairs. All right. I suppose we should do a sine and cosine, but for now, I think that's good. It shows you guys the techniques that we're using and how to use the ratio test to find the interval of convergence. Okay, see you guys.